Welcome to the first module of week 3. Before we go any further, we need to get a basic overview of how the electricity system works. Most important for this understanding is the electricity grid. The grid connects producers of electricity to consumers. In reality, there are many different grids, like transmission grids spanning continents and distribution grids for short distances in cities, all connected together. But we will ignore these details here and instead focus on the key problem. Demand and supply must always be perfectly balanced. This is an important difference between electricity and most other products, like, say, t-shirts. You can store a t-shirt in a warehouse or a container. You can ship it somewhere, and it will take time to arrive. So to a large extent, we could think of a single t-shirt factory as an independent design problem that can be analyzed independently of the rest of the economy. But not so with electricity. It cannot be stored, only consumed or converted into other forms of energy, like chemical energy in a battery. It is transported instantaneously. Supply and demand must always be exactly the same between everything connected to a given grid. So with electricity, it is critically important to consider the whole system of power plants connected together in a grid, as well as all the sources of electricity demand on that grid. Let's look at a very simple case. We have one power plant and a single source of demand. Let's say this is a lamp that I can turn on and off. At the exact moment I turn the lamp on, electricity demand goes up a tiny bit, and the power plant has to work a tiny bit harder to meet that demand. If the power plant is an old school one, like a coal-fired plant, its generator is rotating 50 times a second, so 50 Hertz. When I turn on the lamp, the generator slows down a tiny bit because it must work a tiny bit harder. Immediately, the automated plant controls increase the amount of fuel being burnt so that the generator speeds up again and keeps rotating as close as possible to 50 Hertz. There are many such systems throughout the electricity grid to ensure that when demand goes up, so does supply. And when demand goes down, so does supply. Now, when there is a very large, sudden change, like a storm knocking out an important power line, those systems cannot keep up. Demand becomes larger than supply, or vice versa, and the whole thing falls apart and shuts down. Now, of course, I'm not the only one switching my lamp on and off. A lot of individual actions add up to large changes in electricity demand through time. Here you see daily electricity demand for 3 European countries over the whole year 2019. An obvious first thing to notice is that the total demand in larger countries is higher, but there are many other differences. Germany uses some electricity in heating, so electricity demand goes up in winter. The Netherlands, on the other hand, heats almost exclusively with natural gas, so electricity demand is not influenced much by the seasons. Italy has higher electricity demand in summer because of air conditioning. We also see that there's a strong periodic fluctuation. Demand is lower on weekends. And in holiday season, like August in Italy, many things shut down. So demand is lower, same over Easter or, for example, Christmas. This variability of demand is well understood, and the electricity system is designed to handle it. Let us now look at a typical day in a typical country in a temperate climate area, like, say, the Netherlands. Demand for electricity is never zero, because some things, like infrastructure or industry, are always running. But it does go up during the day as people get up and go to work, and it peaks in the evening as people are cooking, going out, using their devices, and so on. Traditionally, this demand would be met by 3 different types of power plant. The baseload is the demand that's always there. It's met by expensive to build, but cheap to run power plants like nuclear reactors. On the other hand, the peak load is met by cheap to build, but expensive to run plants. Say, a gas-fired power plant that can be rapidly turned on and burns expensive fuel to cover only those few hours when it's really needed. And there's the intermediate load between these two that fluctuates quite a bit and is served by plants that can increase or decrease their output to match these fluctuations. Because the fluctuations of demand are well understood, it's relatively straightforward to run such a system, despite the fact that supply and demand must always be carefully balanced to prevent the whole thing from collapsing. But this simple world is increasingly fading away. The problem is that with the increasing deployment of wind and solar power plants, electricity supply itself is becoming more spread out and variable, in ways that it's much harder to predict than the variability of demand. You see here, in our stylized day, how wind and solar fluctuate quite dramatically and eat into the traditional generators when there is a lot of sun or wind. Unlike the large traditional power plants, many of these solar and wind generators are highly distributed and thus harder to control. And you also have periods when there is no sun and little wind. Concepts like a baseload generator, which is always delivering a fixed amount of electricity, simply do not make sense anymore in this new world. And it becomes a lot more difficult to ensure that supply and demand of electricity are always perfectly balanced. So, electricity demand will go up as more things are electrified: road transport, industrial processes. And as we will see, wind and solar electricity are the most likely sources for this large amount of climate-neutral electricity. This means that building a stable energy supply, despite the variability of solar and wind, is one of the key challenges of building a climate-neutral economy. But before we get to that challenge, for the remainder of this week, we will look more closely at all of the options of supplying climate-neutral electricity and how to quantify their cost, variability, and their available resource.